Hello everybody and welcome back. We're here with the last question, question number 25 on the 2003 Grade 8 Gauss contest put out by the University of Waterloo. So let's have a look, shall we? So in the diagram, a positive integer is to be placed in each of the 9 boxes so that the products of the numbers in each row, column, and diagonal are equal. So this is a very similar concept to something called a magic square, where the sum of each of the numbers in each row, column, and diagonal are the same. Okay? And if you notice, they've already filled out one diagonal for us, so we can figure out what the products of these numbers should be equal to. Alright? Some of the entries are already filled in. Yeah, I just noted that. The number of possible values for n is... okay. So immediately I know n's got to be a positive integer, but there's probably a bit more to it than that. Okay? Looking at our possibilities, there's only so many we can have. First, let's figure out what this number here is, what the product that every row, column, and diagonal should be is. So I'm going to grab my calculator, and we should have 6 times 12 times 24, 1728. Okay, 1728 should be the big number that everything's going to work out to be. So let's draw a diagram over here. It's a little 3x3 picture. So we had n up here. We've got 12 here, 24 here, and 6 here. So 6 times 12 times 24. Of course, if we bring the 2 over with the 6, we've got 12, 12, and 12, so it should be 12 cubed, or 728. Okay. So that's what everything should multiply to be equal to. And we're looking for possible values for n. Okay. What can we do here? Well, surely n can't just be anything. It's got to at least be a positive integer number that, along with 2 other numbers, multiplies to 1728. So it's got to at least be a factor of this number. But will any factor do? Could n be 1728? No, of course not. Because if n were 1728, then we'd multiply it by some number up here, multiplied by 24, and we'd need to get back to 1728. That just doesn't work. If I give these guys some names, let's say A, B, C, D, and E. These are the other numbers. These are the ones I don't know anything about. I'd like to try and at least fill in this diagram. This is something called diagram chasing. It can be quite helpful, especially actually if you go on to do some university mathematics. Homological algebra has a lot of diagram chasing in it. But what we're really doing is we're going to take the limited information that we do know, this 1728, that should be the product of every row, column, and everything, and say, well, gee, if I wanted to get A, that number in the very first row, that's going to have to be A times n times 24 is equal to 1728. I can rearrange that and maybe solve for A. Then I can take that A and the 12 in the middle and try and work out what D should be, because D is the number in the middle of the bottom row. Okay? So we're just going to chase things around. Hopefully we should get the rest of this thing in terms of n. So I notice that n times A times 24 should be 1728. So if I rearrange and just get A, I'll have 1728 over 24 times n. Well, 1728 over 24, that's just going to be 6 times 12. That's 72 over n. So now I have a value for A. Okay? And that was going along the first row. How about the first column? N times B times 6 should be 1728. That's the condition they gave us. So if I want to rearrange, B is going to be 1728 over 6 by n, and that's going to be, I think, 288 by n. I'm going to double check that on my calculator right now. Yeah, 288 divided by n. Okay, so now I know what A and B are. That's great. I can use A and this 12 to get D. So A times 12 times D is 1728. So D is 1728 over 12 times A. Well, that's going to be 144 over A. And that's 144 over 72 by N. That's going to be 2 times N. So whatever N is, D needs to be double that. That's pretty nifty. And we can also work out C by using B, 12, and C. So B times 12 times C has got to be 1728. So C is going to have to be 1728 over 12 times B. That's going to be 144 over B. And B is 288 over N. So that's actually going to be a half N. Okay. So in order for for C to be an integer, we know that N has to be a multiple of 2. That's pretty cool. Otherwise, you would take a half to get C, and you wouldn't get a usable answer out there. Okay. And now E. Well, actually, there's a lot of ways we can get E. We can get E by going N times 12 times E has to be 1728. Or we can, because we now know what C and D are, we can do 24 times C times E, or 6 times D times E, and all of them should hopefully be the same value. If not, we'd be able to set up an equation and solve for N. But let's just double check, because maybe, I know 1 isn't one of the given options, but let's just make sure. We rearrange this one, we get E is 1728 over 12 times N, and that's going to be 144 divided by N. So no matter what, N has to be a factor of 144, otherwise E isn't a positive number. We need to have 24 times C times E. Okay, and that means that E is going to be 1728 times 24 times 1/2 N, and that's going to be 1728 times 12 times N, because the half and the 24 will cancel out to give you 12, and that'll be the same thing, 144 over N, and we get the same thing when we do D and E. Six times 2N. Well, the 6 and the 2 combine to be 12. And we got 144 over N. Okay. So let's put it all together and make another diagram, but now just in terms of N. So down here we'll have 144 over N. 72 over N. 288 over N. Here's N up top. 24, 12, 6. And we have 1/2 N and 2N. All right. So now what can we do? Well, the only other condition we need is that all these things have to be positive integers. Okay? So, for example, as I already said, 1/2 N must be a positive integer. So N must be a multiple of 2. Okay? And that's the only one that gives us a condition like that. 2N, doesn't really matter what N is. As long as N is a positive integer, 2N will be a positive integer. But then we get into these ones, 72 over N, 144 over N, 288 over N. So 72 over N must be a positive integer. And that means n has to divide 72. N is a factor of 72. Likewise, when we do the same thing with 144 and 288, n must be a factor of 144, and n must be a factor of 288. And so you might think we've got a lot of conditions here. And we've got 4 of them. We have to have a multiple of 2. We have to be even. And we also have to be a factor of 72, 144, and 288. But 72 is a factor of 144 and a factor of 188. Or sorry, 288. So as long as n satisfies the first one, is a factor of 72, it'll be a factor of these other ones as well. So since 72 is a factor of 144 and 72 is a factor of 288, we only need n is a multiple of 2 and n is a factor of 72. Great. So we've narrowed it down completely. Factors of 72 is what we're looking at. N has to be a factor of 72. How about we list out all the factors of 72? And once we've done that, our other condition is n has to be a multiple of 2. So we'll just count up all the factors of 72 that happen to also be multiples of 2. And these will be exactly the numbers that work out. Okay? So our factors of 72, and this can be a bit tricky. A good way to do this is to say 72, break it down into its prime decomposition. Just as powers of primes. Multiply it out as powers of primes. And as a little trick, if you have a number written out like this, add 1 to each of the exponents and multiply those answers together, and you'll be able to tell, so this will be 4 times 3, 12. 12 will be the number of factors. So that way we'll know if we've missed one. So factors of 72, you can work these out for yourself if you want to. I'm not doing it in a particularly methodical way. 3, 4, I just tend to just start thinking of them until I can't do any more. So 8 and 9, those are right beside each other and they're multiplied to 72. Everything after the 9 should be something before the 9 with 72 divided by that. 72 divided by 6 is 12. 72 divided by 4 is 18. 72 divided by 3 is 24. 72 divided by 2 is 36. 72 divided by 1 is 72. Now let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All of these are factors of 72, and thanks to breaking it up into 2 to the power of 3, 3 to the power of 2, I know I should only get 12 factors. So that's all of them. There they all are. Okay, and this works with any number. So for example, 85 is 5 to the 1 times 17 to the 1. So 1 plus 1 times 1 plus 1, because we add 1 to each of the exponents regardless of what they are, so that should be 4. There should be 4 factors, and indeed there are. 1, 5, 17, 85. Okay? So that's how that works, and it's quite useful. It's a useful little thing to have up your sleeve. Okay? So these are our factors. Now let's pick our magenta E red. We'll figure out we want multiples of 2. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So our answer is 9. And the 3 that are left out, they're clearly odd. They won't do. So 9. Is 9 one of the possible answers? Yeah, there it is, right in the middle. C, 9. And that's going to be our answer to this one. If you want to, you could double check and say, let's pick one at random. Let's say 72. See if we can figure out what happens to our little chart. This is a great way to check. 72 is a good one because it's a nice big number. If something were to go wrong, it would probably go wrong with 72. This is where A was. He's got to be 72 over 72. He should be 1. We've got 24. We've got 12. We've got 6. This one here was 288 over 72, so he's got to be 4. This one down here has got to be twice 72, so he's got to be 144. What else have we got? This one over here is 144, so this has got to be 2. 144 divided by 72, and this one's a half 72. That should be 36. Does this all work out? Well, let's grab ourselves our calculator and just pick some rows at random. How about 24 times 36 times 2? 1728. 6 times 144 times 2? 1728. You can check, and this is all going to work out. Okay. And what we could even do, if we have time, and we want to convince ourselves that, yeah, we definitely need that multiple of 2 requirement, we can actually take a look at, say, what would happen if n was 3? Why does this fail when n is 3? And it's going to fail over here, because that was the 1/2 72, but we can have 3, and we'll get 24 here, another 24, 12, and this one down here is going to be 144 divided by 3, so that's, that's 40-something, 48, I think. Yeah, 48, so that'll be 6 over here, 18, so 288 divided by 18, I cannot do that off the top of my head. It's going to be 16. 24, 12, and so this should be 6 down here. And now, what should go here? Okay, our math says it should be a half 3, but what if we just did 1728 divided by 16 divided by 12? We should get a 9 here. I did something wrong. Oh, this isn't 288 divided by the other 2. This is 288 divided by 3. So 288 divided by 3, 96. So this row should be 1728 divided by 96 divided by 12, and that should be 1.5, not an integer. Okay. So we've done a little bit of extra check, and we verified that, yeah, the odd ones don't work, and even something as ridiculous as 72 will work. Okay. So our answer is 9C, and that about does it. So thank you guys for watching. This has been a wonderful contest. Hopefully you've enjoyed it as well. And I'll be moving on to some of the grade 9 stuff from this year in the next couple videos. So stay tuned for that, or if you're looking just for another Gauss 8, I'm sure one will be up shortly, and you can take a look at that as well. Of course, if you don't like how quickly I'm putting things up, you can click the link in the description, go to all of Waterloo's past contests, and try all those contests before I get to them, certainly. Okay? So, that's it for now. Have a wonderful day, and I'll see you guys next video.